The purpose of this video is to cover troubleshooting fundamentals and advanced strategies for solving problems that you may encounter in the real world. As a .NET architect, I've been solving problems for over 16 years and attacking problems that weren't even in the programming domain. So my experience is in order to survive on these incredibly difficult troubleshooting endeavors, I've had to come up with some very sound practices for strategizing and solving these problems. So what I'm covering today it goes beyond just development and can be applied to other domains that are technical. There are three fundamental pieces of an optimal troubleshooting strategy. The first is to gather information. You have to have information at your fingertips in order to make decisions on where to go next or how to assess the situation and to get a perspective on what the probabilities are for different possible causes for a problem. Another piece that is fundamental is to validate assumptions. It is very easy to overlook this step and start attacking a problem and get very deep in the weeds and miss some basic things that if you would have just checked some assumptions, you could have solved the problem very quickly upstream without going through an incredible amount of effort. And then the third piece for an optimal strategy is systematic changes. As I'll describe later, you can go about troubleshooting in a variety of different ways, and some people take a chaotic approach, which is just shooting a weapon in any direction and hoping they hit the target. And the optimal approach is to do it systematically so that you get to the end goal of solving the problem much quicker. So for gathering information, there are many pieces to this. The most common ones I put here, and I can't stress enough, you have to look at the logs. You've got to look at the logs to collect information. It's very easy for people to overlook that logs are a crucial piece of information that can give you insights into where to look next or whether or not there's actually an issue happening or what that issue could be. So look at the logs and get timestamps. Other pieces that are important are checking to see, is the issue reproducible? Was it ever previously working and when? Versions are important for different systems, and that's not specific necessarily to software. It can just be other components that you may be troubleshooting. Identifying changes in the environment and configuration and changes in code and changes in user workflows and processes and how the software is used. And if it's not software, how the machine or how the technical system is used. All of those can impact a problem. The second fundamental for troubleshooting is validating assumptions. And this one is by far not only it's both easy and it's hard. And what makes it easy is that it doesn't take long to check configurations and binaries and versions. And those are things that in our mind we assume to be correct, but more often than not, those are the actual reasons for the problem. And this is what makes this step hard, is that assumptions are virtually invisible. In our mind, we think they are correct, and therefore we don't see them. So understanding and recognizing and knowing what the assumptions are and going ahead and validating those are a very crucial step to identifying a large set of issues when it comes to troubleshooting. The third piece for troubleshooting fundamentals is systematic changes. And I've got this diagram here. It shows that a junior strategy for solving a problem is a lot of work versus a senior or even a wizard that their process for troubleshooting is so efficient that it doesn't take much work for them to identify the problem and fix the issue. So let's talk about these systematic, or lack thereof, these changes. A junior engineer, what I see a lot is they will experience a problem. They've got their system in a state where it's not working, and then they'll start making changes, and they'll just the changes that they'll be making to try to fix it are virtually random. There may not be much thought into them. They'll just be trying one thing and trying another, and it leads them all over the place, they trample over previous data points where they could have been moving closer to a working solution, but instead they weren't really paying attention, and they lose all history of those steps that if they would have looked at that information, it could have been useful insights into telling them that they're getting closer to identifying or closer to getting to a working solution. And ultimately they circle around and spin around till they get to a dead end, and they throw their hands up and they have to reach out to a more technical superior that can solve the problem for them. And one of those might be a senior engineer. And the strategy they usually employ is they'll start out with a not working state, and they'll make changes in a more systematic way where they'll make a change, and then they'll see, okay, this is a viable change that gets it to more of a potentially working solution. And then they'll make another change and realize that had no bearing on this problem, so they'll back out of that and get back to their original state. And then they'll make another change, see that doesn't really matter. And then they might make a third change and identify, okay, this might have something to do with it. And it's almost like they can smell that this change that they're making is getting them closer to a working state. And then they just kind of repeat this process till they ideally eventually get to a working state, and they identify what is the root cause of the problem. Now, a wizard, a troubleshooting wizard, is somebody that right out of the gate, they try to get the application back into a working state. They restore the original app. They do whatever it takes to get to a working state. And the advantage of this is instead of starting from a broken state and working backwards to a working state, if you start at a not working state and you're working backwards, there's a potentially long list of things or changes that you need to do to get back to a working state. Whereas when you start from a working state and you're making changes, you can do things in a way that you can get better recognition and faster identification of what change or what is the actual issue. So first, you get back to the working state. Next, you start making some changes and you identify these changes and what impacts they have on the system, and you review them and you systematically apply them until you get it to identify which change is the one that caused it to stop working. And another a step further is to do this in a binary process. So if you start out in a working state and there's a potential where you can make 5 incremental changes to get it to a broken system, then you can start with making a change in the middle out of these 5 changes. And if, depending on whether it works or it doesn't work, you can then go back and skip back steps, skip back changes, make a change and seeing, okay, is that the one, or okay, do you need to fall back and take another step forward? And this binary approach can significantly reduce the amount of time it takes to identify which one of these changes was the is the root cause of the problem. So when you try this, sometimes you don't have the ability to get back to a working app. And if you don't have that capability, then another strategy is to just build an isolated working solution, create a console application, create a standalone web application, get back to a working state, because it's that original working state that gives you 2 perspectives on the problem versus just one perspective, which is the not working state. And when you're looking at a problem from the not working state, it is really hard to see the forest for the trees. And that's why these 2 perspectives are important. So with that being said, I want to talk about the example problem that was really the driving factor for this video. And it was a very fascinating problem that I actually didn't even follow this guidance that I have in this video. I was so fascinated by this problem that I was really just shotgun approach, looking at all sorts of different aspects of this in not much of a systematic way. But I wanted to look at this thing not to try to solve the problem as fast as possible, but to really understand how all of these changes would affect this problem. And the problem that I was experiencing was in a C# application, a non-blocking method was blocking. And that is a very fundamental piece of software development is you have a method and you call this method and it's either a blocking method or it's not. And a little more specific here is that I had a .NET worker thread was being blocked when I was calling an SDK from Microsoft's Azure Storage library. They've got a storage SDK, and I was calling a getMessage method. And it's a non-blocking method. It should never block. So why it was blocking had me truly fascinated. And so the stack trace for this is that doing a request to get message down into the bowels of this SDK, it's blocking on this on a wait for the monitor, and there's really no reason why it should be waiting or blocking. And so to get even more fundamental, I tried some other SDK methods, which I'll talk a little bit about later, but the method above is also another non-blocking method. It's just checking to see if a queue exists. And that was blocking as well. So something was really fundamentally wrong with my application, why I was blocking when it shouldn't be. So the architecture for this problem is that I had a web application that was writing messages to a queue, an Azure storage queue. And then I had a very simple .NET WinForms app that was polling this queue and reading messages out of this queue and just feeding these messages off to some worker thread. Now, none of that is important. What's important is that I just had a simple thread that was reading these messages, reading this queue, and every time it pulled off a message, it would feed it off to another worker thread, and then just continue reading from this queue. But reading these messages should not be blocking, but it was. Some data points for this is that when I was running it on my own machine, getMessage was not blocking, it was working. And I had copied the binaries and configs to the environment, this virtual machine for which I had this application running. And this getMessage method was blocking forever on this virtual machine. It never unlocked. So the strategy that you typically employ, or that I employ for these kind of situations, is I build a mental model of like a probability buckets. So here I have a variety of buckets on what could be the possible cause of this issue. And I'd copied the binaries and the configurations onto this virtual machine. So I had those at I never put anything at 0%. So just for purposes of simplicity in this video, I will put them at 0%, but I would have put these at 1% for the binaries in configuration. I really had no idea what could cause this. I just had to guess that this was maybe a logic bug in the application, and it could have been any of these other things, like something going on with the .NET or the virtual machine or something in the environment. Maybe it was blacklisted by Azure, and maybe it was blocking for some reason that I didn't understand. Maybe there's a bug in the Azure SDK. Maybe I was misusing the task parallel library, or maybe there was a race condition and it was blocking for some reason that I didn't understand. So the first thing, I needed more logging. I put some logging in there, and after that, the best I could do is guess that it was a 50% chance I just got a logic bug somewhere. The next step, I actually attached a debugger, and that's how I got that call stack earlier. And with that, it became clear that I didn't really have a logic bug, and it had to be something else. And the way that I had this polling thread functioning, I deduced that it was maybe misuse of the task parallel library. So the way that I was starting this thread, maybe I was starting in a thread that I was starting in a way that wasn't ideal. And so I gave that a higher probability of the issue there. Next, I tried different SDK methods just to kind of rule out maybe an Azure SDK bug or something like that. And that had no effect. So I went ahead and refactored the use of the task parallel library to do it a little more fundamental and more best practices for the threading. And so that reduced the probability that it was task parallel library misuse. And at that point, I just surmised that maybe it was just I'm getting blacklisted by Azure. So that was the highest probability. And to eliminate that, I created a new WinForms app. That's that siloed application that we were talking about before. And sure enough, that worked just fine. So that had me kind of stumped, and it definitely, I wasn't being blacklisted by Azure. So maybe, okay, it could have been a logic, environment, SDK, TPL misuse, race condition. It could have been any one of these things. I had no idea. So I just went the fundamental route and moved some code to the app startup to see, okay, if I put this in the beginning of the app rather than calling the get message in an actual thread, if I put it into the beginning, does that change the behavior of this problem? And sure enough, it did. The problem went away when I just moved this get message call to the beginning of the app. So that made me think, okay, what is... Is there something going on with the environment or something with the logic that was very fascinating to me? And I started moving the code around, and I went from, this is that systematic approach from going from a working state to a non-working state. I moved it from the code in the startup. I moved it deeper and closer to where it was in that thread to the point where I eventually got it to break somewhere between startup and the thread. And that led me to believe that, okay, it wasn't the misuse of the task parallel library. There wasn't a race condition here. I'm not being blacklisted. Maybe there's still a logic bug, but it's got to be something like the environment or the Azure SDK, because that just doesn't make sense that you move it to the beginning of the startup, it works, and then you move it to the end of your startup, and just a simple SDK method stops working. So I tried upgrading the Azure SDK, and that had no impact. It still broke in the same way. And so I just bumped up the probability that there might have been an environment issue. And so because of that, I updated to .NET 4.8. That had no effect. It still broke in the same way. So I was at a loss for what could possibly be the issue here. And then I copied the code over there, the source code, and ran it from Visual Studio. And sure enough, that same code worked from Visual Studio, completely worked. And that kind of blew up all my probable causes. And now I'm thinking, well, was I running the correct binaries? Did I have the correct configuration? So I started rethinking all of those assumptions. And I went ahead and dug up the original application. And sure enough, the original application worked. And there weren't really any changes between the original application and the broken one. So the possibility that it was logic was significantly reduced. And it's not the environment, it's not black. All these other probable causes are now virtually zero. It had to be something with the wrong binaries or wrong configuration. And I was putting my money on the wrong configuration. So I went ahead and updated the config for the broken application. And that is actually what was the issue. Is it turns out that in the broken application, the binding redirect for the system runtime compiler services was incorrect. And what I mean by that is the working application had a redirect of 4050, but my broken application, because of some other changes that I'd made updating some packages, actually had a slightly older version binding redirect. And what blew me away is that I never would have guessed that this version difference here would cause a method that is never supposed to block. And that's what happened. And that is why validating assumptions is a very key portion of troubleshooting fundamentals. And that leads us to what I call Kerr's Law. Kerr's my last name, and I jokingly called this Kerr's Law many years ago. And every time I would counter a scenario where I became convinced that all the pieces were correct, yet it still wasn't working, 99% of the time, the reason why it wasn't working was because of a flawed assumption. There was something in one of my assumptions that I just couldn't see that was incorrect. And I've become much better now in recognizing these situations. And once I recognize that, okay, all the pieces look like they're correct, but it's still not working, that's when you got to slap yourself across the face and say, okay, double check, triple check, expand your browsing of these assumptions and validate as many as possible, and try to find those invisible assumptions and validate them. And that has allowed me to solve many difficult problems in a short amount of time. And for this particular problem, I didn't do that, but this would have identified the problem very quickly instead of the entire day that it took me to identify this problem. So to recap, the 3 pieces for troubleshooting fundamentals are gather information, validate assumptions, and do a systematic approach for making changes and getting to a working or back to the working or non-working state.